I'm going to talk today about what are the instructions that we need in a given architecture for doing integer multiplication and division. So today I would like to talk about these instructions, okay, in the MIPS architecture. So in the case of integer multiplication in MIPS, we can multiply any two registers. RS and RT are my source registers. And when we multiply, when you multiply two 32-bit values, you get a 64-bit product. So there is a multiplier in the hardware, which is implemented inside the MIPS processor that does the multiplication. The multiplication can be signed or it can be unsigned. So there are two different instructions. We have mult. So mult is used for signed multiplication. Let me use my highlighter. So mult here means multiply, and this is used for signed integers. So we are multiplying two 32-bit integers, RS and RT. So here my registers are 32 bits because I'm assuming that my architecture is 32 bits. So my data is 32 bits. We can do it the same thing for 64 bits. If my registers are 64 bits, it will be a 64-bit multiplier. But okay, so all our discussion here will be about 32-bit architecture, not 64-bit architecture. So in the case of mult, we do signed multiplication. There is also mult-u that does unsigned multiplication. Okay, so the difference is in the product. The product can be signed or unsigned. So mult is going to produce a signed product, whereas mult-u is going to produce unsigned product. Now the product will be 64 bits. When you multiply two 32-bit values, you get a 64-bit product. Okay. And therefore, in order to produce a 64-bit product, the way that it's defined in the MIPS architecture, they use two registers, high and low. So they have two special purpose registers, high and low. High will be the high order 32-bit of the product, whereas low will be the low order 32-bit of the product. So we store the product in two registers. This is how it was defined in the original MIPS architecture. There are revisions of the MIPS architecture, and in the latest revision, they can store the result directly in a general purpose register. In fact, MIPS has a special mul instruction, okay, that can compute only the low into destination register RD. So the mul here, okay, is going to multiply RS by RT and writes the result only into RD. So it will copy only the low into destination register RD. It's going to discard, okay, the high 32-bit of the result of the product. So use mul if you are multiplying, let us say, small 32-bit. If the product is small and it can fit in 32 bits and you don't really need the high, then in this case use mul to multiply two registers and to have the result directly in a general purpose register RD, okay, without the need to use high and low. Okay, so let me talk about integer division. Similar to the multiplication, we have two divide instructions. We have div and we have divu. So div is used for signed division, whereas divu is used for unsigned. So remember that these are two different operations, and the result will be different. So if you are dividing signed integers, you have a signed quotient and a signed remainder. So we need two results. And again, we are going to use the same registers, high and low, in the case of division. So high will be the 32-bit remainder, and low will give me the 32-bit quotient. So if we use div, the remainder and the quotient will be signed. They can be positive or negative. And in the case of divu, the division will be unsigned and the remainder and quotient will be unsigned. Okay, so we get two results in two different registers. Okay, and these two special purpose registers, high and low. Now, in programming, what you need to do is that you need to use the general purpose registers. So therefore, we have two instructions here that can copy the high and low from, we can copy the data from high and low into any general purpose register. So we have moved from high. You can copy the value of high into register RD. So my destination is RD. And I have moved from low, where you can copy the value of low into RD. Okay, so you have moved from high and you have moved from low. So these two instructions are essential after doing multiplication or doing division, and you would like to copy the result into a destination register RD. So the first instruction is going to copy high into RD, and the second one is going to copy low into RD. Okay. So these are the instructions. This is a summary of these instructions. So we have mult, we have multu. Notice that these are, they have the opcode equal to 0. They are of the R type. Okay, so we multiply RS with RT. We don't write the result into RD. Notice that RD equal to 0, indicating that the result here is not written into RD. In fact, we write. And the instruction has a special function code, okay, for mult, and a different function code for multu to distinguish between signed versus unsigned multiplication. Okay, the mul instruction was later added to the instruction set, and it can write the result directly into RD. So therefore, notice that here we have RD. Okay, it's a different opcode and a different function code. That's the mul instruction. We also have diff and divu. Okay, they divide RS by RT. So RS here is my dividend, RT is my divisor, and we write the high and low. So a pair of registers here, the special purpose high and low registers. Okay, so high will contain the remainder, low will contain the quotient. Div will do signed division. I'm putting here small s to indicate this is signed, whereas divu is going to do unsigned division. Okay. And again, they use the same opcode 0 because they are of the R type, and special function codes for div and divu. Sorry, divu here. Okay. Note from high, move from low, because you would like to copy the values of high and low into any destination register RD. Notice that we are not using RS, we are not using RT, so these are just zeros. We copy the value of high into RD, or we copy the value of low into RD. We are using special functions for these. Again, all of these are of the R type, the same opcode 0. And finally, we have move to high and move to low. And you can copy in the other direction. You can copy the value of register RS. RS here is my source register. You can copy it to high, or you can copy it to low. Again, the same opcode 0, but we have different function codes. Okay. And these instructions do not cause any arithmetic exception. So in the case of multiplication, we get a 64-bit product, okay, which is exact, and therefore we cannot really have overflow, because when you multiply two 32-bit integers, okay, the product cannot be longer than 64 bits. So 64-bit product in high and low. In the case of division, let me say something. Okay, you should not divide by 0. You should not divide by 0 because the division by 0 is undefined. But the hardware is not going to cause any arithmetic exception if you divide by 0. So if you are programming, you as a programmer should not divide by 0. You should really check the value of the divisor before division. But if you do divide by 0 and you would like to try it, it can produce for you any result. Any garbage result will be produced, but this result, of course, will be incorrect. Okay, so you as a programmer should not divide by 0. So the hardware does not really cause any arithmetic exception, even if you divide by 0. So the way that the division instructions are defined is that they will compute something, okay, even if you divide by 0. So depending, of course, on how the hardware is implemented, the result of division, of course, will be undefined if you divide by 0, but there is no exception. Okay, is this clear? So these are the instructions that exist in the MIPS architecture for integer multiplication and division. We have seen 2 special purpose registers, high and low, and we have seen the instructions that will copy the value of high and low into a destination register RD, or they copy the source register RS into high and low. Okay, questions?
Doctor,
Oh.
I think in Java or other programming, if you divide by 0, there is exception in compiler.
Of course, yes.
Why here is not?
That's the way that the hardware is implemented. Okay, so of course, in a high-level programming language, the compiler can generate the instructions that will cause the exception. That's always the case when you are translating a program. So the compiler can do the checking for you. Yeah, and in other words, when you translate the program from a high-level programming language into a low-level programming language, okay, you can let the compiler to generate additional instructions in your program that will cause an exception if you do divide by 0. So at runtime, these instructions can check the value of the divisor, and if you are dividing by 0, it can generate an exception and transfer the control, okay, to an exception handler. But in the case of the architecture, the hardware, okay, so here the hardware in the MIPS architecture, okay, they do nothing, okay, and leave it to the programmer, because you can always detect this in programming. You can always check the value of a register, whether it's 0 or not 0, and take an action based on this. Okay.
Okay.
So for simplicity, let us say that for simplicity, the designers of the MIPS architecture did nothing. Okay, so even if you divide by 0, basically the hardware does not really care. It's not going to divide by 0. It's going to just to produce, okay, a garbage result and continue. Okay, so we say that the result is undefined. So the hardware does not define the result if you divide by 0, but of course the software can do something about it.
Oh, okay.
Let me talk about this example here. Okay, so now we understand the multiplication, the multiply, and the divide instructions. Suppose I have a string, okay, and I would like to convert this string into an integer. Now, when you, let us say you ask the user to enter an integer from the keyboard, okay, so there is a system call that can read the keyboard, and it will store the value of the integer in a given register. Now, when you ask the user to enter an integer from the keyboard, okay, the user is going to type keys, okay, digits on the keyboard. Now, how do you think these keys will be entered? When you press keys on the keyboard, what will happen? Students?
It will give
Are you thinking? Are you thinking? I really need everyone to be involved in this discussion. Okay, so when I press a key on the keyboard,
every key is represented by hexadecimal or by 0 and
so
1.
These keys are characters, right?
Yeah.
So for example, if I press character A or character B, it could be capital, it could be lowercase, or it could be like a special character like parentheses or anything. Okay, even digits 0 to 9, these are characters. Yes, Mushtaba, tfadda.
I check whether they are these characters are digits. Then I subtract 13 30 from the
Yeah, we'll talk about
30
these
hex.
details. Yeah, I'm coming to these details, but before that, we have to understand, you agree with me that these characters that exist on the keyboard, right? These
Yes.
are characters, right? These are characters, and each character has a code. Your input, which is supposed to be an integer, is an array of characters. Good? Do we agree about this
Yes,
point?
good.
Okay.
Yes.
Yes, we agree.
So this is not even a number. So what I really would like to do now, I would like to take this string and convert it into an integer. Okay? I would like to have this string of characters, I would like to convert it into an integer. Now, this integer will be represented in what system, number system? This integer will be what?
Binary.
It will be a binary number. And I would like to have this binary number as just one number inside a 32-bit register. Good?
Yeah.
Yeah.
So I have my input, which is a string, and I would like to convert it. I need to write a function. So this function exists inside the system call. So the system call is doing this automatically for me. But now I'm going to write a function that does it. Okay? So we're going to write a function specifically to convert the string of characters into one binary number. Okay? And this binary number will be the integer value of this string. So we call it string to integer conversion. Okay? So how do you think that we are going to convert this string to an integer? How do we do this? How do I convert this string, which is 91052? These are the characters. How do I convert it into one number in binary? Fadal Mustafa, yes, you raise your hand.
Yes, as I said, I convert each one. I check whether each one is a digit.
Yes.
Then I subtract 30 hexa from.
Yeah. So we know that
30.
actually exactly. So character 0 has a character code. I can check this character code for the character 0. Okay, it is 30 in hexadecimal or 48 in decimal. So what you can do is that you can convert character 0 into the number 0. You can convert character 1 into the number 1 by doing a simple subtraction, which is -30 in hexadecimal or number 48 in decimal. So if you enter character 0, you are actually entering the number 48. So 48 minus 48 will give you the number 0. If you press the character 1, you are entering 49. So 49 minus 48 will give you the number 1. And so on, okay? So we have these converted the individual characters into numbers, but I still need one number for the entire string. So Mushtaba, what you did is that you did not solve the problem completely. You solved it partially. I need to convert the entire string into one number.
You mean, Doctor?
I need
we need the number 91052.
I need so the number will be 91,052. I would like to have it in binary. This number, I would like to have it in binary. That's what I mean. Fadal Khalid, you raise your hand.
Yeah, we need to use multiplication. We should give
how
every digit its for example, if here we can say we can see 5 in العشرات in Arabic.
Yes.
So we need to multiply.
We call it tens. Yeah. So we have to. Yeah. So 2 will be just 2. 5 will be multiplied by 10. 0 will be multiplied by 100. 1 will be multiplied by 1,000, and 9 will be multiplied by 10,000. How do I do this algorithmically? I need to write a function. Fadal, yes.
We shift the bit.
Shift. This is an array.
Do I know what the size of the input of the string?
No, it could be anything. It could be 4 digits, 5 digits, 6 digits. It does not really matter. You know that in the case of an integer, you can have the longest integer having like 9 digits or even 10 digits, because a 32-bit number can be quite large. A 32-bit register can store like 4 billion something if you look at the number as unsigned.
So I can take the index of the enter, then I traverse back, right?
Yeah. So when I enter, okay, let me put it this way. When this user types these digits, which digit is typed first?
The 9.
Yes. So the user is going to type the 9. Then he's going to type what? The 1.
1,
and it's
0, 5,
right? We agree in this order. So if you are going to store it as a string, then the 9 will start at index 0. So you have to start with the 9, because this is the first digit that was entered by the user. So start with the 9. Go ahead. Tell me how you are going to do it now. I need a solution. Omar.
I don't know.
Tafadhal, Omar.
I think we start reading from the left. First of all, when we enter a second number, we multiply 9 by 10. When we enter another number,
so you multiply the 9
again
by 10, and you do
yes.
what? So the first I have 9.
At the end, we sum them up.
Okay.
It will be 9,000 plus 1,000 plus.
Okay, let us start step by step. The first thing that was entered by the user was the 9. So we convert the 9 from a character into the number 9. So we said that we are going to subtract, okay? We are going to subtract the character 0, which is 48 in decimal, right? So we subtract, we get it the number 9. Now this is the first digit. So if the number is just 9, we are done. But if the user enters 1, then this 9 must be multiplied by 10, and then we add 1. Correct? So we get 91.
Yes.
Right. If the user stops after 91 and presses enter, we got the number 91 in binary. So what we have to do is that we have to write a loop that will compute the value of this string in binary. That does the arithmetic. So this is what we call the conversion function or the conversion procedure. Okay. So we are going to take the 9 multiplied by 10, and then we add to it 1. So we get one number, which is 91 in binary. So if the user enters 0 after that, the 91, which is stored as one number in binary, we have to multiply it by 10. So it becomes 910. And then we add the 0 to it, it will remain 910, because the digit that was entered by the user was 0. If the user stops, we have 910. But if the user enters another character, which is 5, it will be converted to the number 5. So the 910 must be multiplied by 10. It becomes 9,100. And then we add to it 5, it becomes 9,105. And if the user enters 2, so the 9,105, which is now in binary, is multiplied by 10, and then we add to it the 2. So it becomes 91,052. Okay? So the idea is, whatever is the value that we have in it, we have converted inside the register, multiplied by 10, and add to it the value of the next digit, and repeat in a loop until the user presses enter, or we reach the end of the string. And if we have entered all the characters in a string, the string must be terminated with a null character. So once we have reached the null char that marks the end of the string, you terminate the loop, because we are converting the string into an integer. So we can ask the user to enter all the characters one by one, and we store them in an array of characters, because the string itself is an array. So we start here by storing the 9 at index 0, then we store the 1 at index 1, and so on. Yes, Khalid, tafadhal.
Doctor, what happens to the null character?
it is 0, I think, right?
Yeah, so the null character is a special character that has the code equal to 0. It's different from digit 0. Now, digit 0, the character 0, okay, has the code 48. Because if you look at 30 in hexadecimal, it's the number 48 in decimal. So the code for character 0 is 48. It's not the null character. The null character is a control character which has the code equal to 0. It's a byte that has the value 0. So we can actually use it to mark the end of the string. The user might press the enter key, which has a special, also it's a control character, the enter. When he presses the enter key on the keyboard, it is also a control character. Okay, so we have a number of control characters that exist on the keyboard, like for example, enter, delete, backspace, tab. All of these are control characters, by the way. Okay. So you can check the value of their codes to detect that if the user has pressed, okay, this enter key to mark the end of the string. So first we have to store all of these characters in a string, and then we have to convert the string into an integer. So here I'm showing to you how we convert the string into an integer. So I'm going to initialize sum. Sum here is my accumulated sum. This will be my integer value. So my integer value will be sum. So I'm going to initialize sum to 0, because if the user just enters 0, that's actually is my sum, and we are done. Okay, so sum is 0, and then we start to load each character of the string into a register. Then we check if this character is in the range from 0 to 9. Then we convert the character into a digit in the range from 0 to 9. So the character 0 will have the code 48, so we convert it into the number 0. And character 1 will be 49, so we convert it into the number 1, and so on. And then what we do is that we do this simple computation. We say that sum is equal to sum multiplied by 10 plus digit. So the existing sum has to be multiplied by 10, and then we add to it the next digit in the string. So this is why we have to initialize sum to 0. And then we repeat until we reach the end of the string. Or sometimes we stop if we encounter a non-digit character, because sometimes if there is a letter, let us say, inside the string, we say that this is not a valid integer. Okay. So if we encounter a non-digit character, then we stop. And that's it. So if you take it character by character, we start here at 9. Okay, this will be my first character. So here the leftmost character will appear as character 0 if you are storing it as an array. So this will be at index 0. Okay, so you will have the string itself in memory as an array of characters. So you start here by multiplying sum is initially 0. So you multiply 0 by 10 and then add to a digit, you get sum is equal to 9. Then when you repeat, you have 9 multiplied by 10, it becomes 90, and then you add to it the next character, which is 1. So it becomes the digit 1, it becomes 91. Notice that 91 is computed in binary because the hardware itself is designed to do all the arithmetic in binary. So addition is done in binary, multiplication is done in binary, everything done inside the ALU is done in binary. Inside the hardware is designed to do all the arithmetic in binary. Then we get 910, then 9105 after encountering the 4th digit, and 91,052 after encountering the 5th digit. So we do it in a loop, okay? And this is my conversion procedure. I can write it in assembly language as shown in the next slide. So I'm calling here my function, I'm calling it string to integer. So I can give it a label. So this label is the name of my function. It's going to convert the input, which is a string, into an integer. You can call it whatever name, this is just a label. Now the input here will be A0. Now A0 will be the address of a string which is null terminated. Null terminated, it means that we have to mark the end of the string with a null character because the string can have a variable length. Okay, depending, of course, on how many characters we have inside the string. And the output will be V0. Okay, me just go back here. So the output will be V0. This is the value that is going to be computed by this function. Okay, so this will be the unsigned integer value. So I'm going to assume here that my integer is unsigned, although we can modify this function to deal also with signed integers. Yani, for example, if the user enters negative, let us say -5, we can actually convert it from +5 to -5 by taking the by subtracting it from 0. So we can also deal with negative integers if you'd like to have a sign, a negative sign at the beginning of the string. Okay, so we can allow even negative integers, not only positive integers. But this function only converts an unsigned integer value. And there is no sign at the beginning of the integer. So in order to do this conversion, I'm going to write a loop. So we have to repeat. So initially, I'm going to initialize V0 with 0. So V0 here is my sum. Okay, so I'm going to initialize it to 0. I'm going to initialize T0 with 10 because I would like to multiply by 10. So I'm going to place the constant 10 inside the register, which is T0. I'm going to use load byte because I really would like to load these characters from memory. Because when the user enters the key, he presses the keys on the keyboard and presses enter, I will have my entire string. I will have it as a string in memory. Okay, so load byte, we are going to load one character. So byte means that one character, 1 byte. We are going to load it from A0. A0 is the address. Okay, the address of the string in memory. So we load it from this address into T1. So now T1 will be the value of this character. Remember that the character itself is represented by a single byte. It is an integer. Okay, so we use load byte. Now I'm going to check if this byte is less than character 0. Then we are done. So we here, when we say done, it means that we just exit the loop. Okay, and if it is greater than character 9, we are also done. It means that if it is outside the range, if it's not a digit from 0 to 9, then خلاص, terminate the loop. Okay. Now, once we are done, if we are not done, yani if we have a character between 0 and 9, then we go. So if we don't branch, we come to the next instruction. Okay, and we add -48. So basically, we are subtracting 48. So to convert the character into a digit, then I'll multiply. I use the mul instruction to multiply V0 by T0. So I'm going to multiply my sum by 10, place the result again in V0 because I would like to have my final result in V0, and then add to V0 the value of T1, which is my digit. So in T1 here, okay, when I converted my character into a digit, I placed the result in T1. So add sum. So I'm computing that sum is equal to sum multiplied by 10 plus digit. I'm going to place this sum again in V0. This is the result in V0. Increment A0 by 1. Notice that I'm just add immediate here. Why? Because I would like to point. This is the address. So I'm incrementing the address by 1. This is address calculation. So I'm just pointing to the next character in my string. And then jump back to loop. Okay, L1 here. This is the beginning of my loop. So by jumping here to L1, then we are repeating this loop, of course, until we encounter any character which is not between 0 and 9. Notice that if we encounter the null char, then it will be less than character 0, and we terminate. We jump to, we branch to done, and we are done. If we encounter any letter which is outside this range, or any character which is not from 0 to 9, we are done. Now, the last instruction in my function is a jump register. I did not talk about this instruction. I'll talk about it, inshallah, in my next lecture when I talk about functions. So this instruction is going to return, from the function back to the caller of this function. Okay, I'll talk about functions, how we make function call and function return. I will explain it in my next lecture. It's very simple, function. It's just a loop, a simple loop that will convert a string into an integer. The integer will be in binary. and the value of the integer will be returned in V0. Okay? Any question about this? Is this clear?
Yes.
I have
But Doctor, I have
Yes.
another question.
Yeah, تفضل.
Why or when we will use mult instead of mul?
Well, if you need a 64-bit result, okay, and if you care about the 64-bit product, then you need the high and the low, then use mult. But in this case, we are restricting to 32 bits, okay? So the product is not going to exceed more than 32 bits, then use mul, okay? So here I'm using mul, assuming that the high register is 0, okay? And the product can fit in low, okay, in a 32-bit register. So we're going to copy only, so this mul does the same thing as mult, but it's going to copy the value of the low register into V0 and discard the high. Okay?
Okay. Yeah. But if, Doctor, I have a large
But
number.
if you would like to get the 64-bit product exactly, you have to copy the low and the high into a pair of registers.
Then I add. Then how I can get
Well,
the full?
you move from high, move from low, you can move them into temporary registers and you can start using them. Of course, the coding will become, so your product will be 64 bits. Okay. طيب, let me show you another example. طيب. So this function is essential because when you enter the input will be a string, and then you have to convert it into an integer, right? And the integer will be in binary and stored in one register, a 32-bit register. That's when you do the input, okay? How about doing the output, the opposite? Okay, when you would like to print a string, okay, or you would like to print an integer, okay, on the string on the screen. So what you need to do is that if you have an integer that you would like to, let us say you would like to print it, you cannot print it in binary, okay? You have to convert it into decimal, into a decimal string. So in this case, what you need to do is that you need to convert the integer into a string, and then you can display each character, okay, of this string on the, let us say, on the display. So the question is, let us do the conversion differently. So in the first example, we converted the string into an integer. Let us do it the other way around. Let us convert the integer into a string. So that's actually is essential when you would like to print an integer, because you cannot really print the bits. What you have to do is that you have to print the digits. And in order to extract these decimal digits, you have to do a conversion. You have to convert it from a binary number into a decimal number and store them as characters in a string. This is the importance of this function, which is the integer to string conversion. So the question is, how do I convert a 32-bit integer into a string? I'm going to assume here for simplicity that my integer is unsigned. With a simple modification, we can also do it for signed integers, and we can deal also with negative numbers, no problem. Okay, if the number is negative, we can convert it to positive by subtracting it from 0. So this will be like the 2's complement. And then we can convert the positive value into a string, and we can insert the minus sign, no problem. But for simplicity, let us assume that my 32-bit integer is unsigned. So let us convert an unsigned, a 32-bit unsigned integer, which is in binary. Let us convert it into a string. Can you do this? Can you extract the decimal digits from the register? Yes, Khalid, تفضل.
We start by dividing by 10 and then taking the remainder from the low register and adding to it a 30 hexadecimal. So we convert it to a character.
Yes, thank you. So therefore, what we have to do is that rather than doing multiplication, we have to do division. So this is the importance. So we have to use the divide instruction. But when you divide, you get a quotient and the remainder. So when you divide by 10, the remainder will be from 0 to 9, right? When you divide your integer by 10, you get a quotient and the remainder, but the remainder has to be between 0 and 9, okay, when you divide by 10. So you can look at the remainder, which is in the high register, not in the low. The remainder will be in high, the quotient will be in low. So you need both the high and the low, okay? So you take the remainder, which is in the high register, and you convert, you move it into, let us say, a general purpose register, and then you convert it into a character, and you store this character in the string, okay? And if the quotient is different from 0, you repeat. You do this in a loop. And therefore, you can extract the decimal digits from a binary number. So what we are doing is that we are doing a conversion. We are writing a conversion procedure. We are writing a procedure that does the conversion. If you remember from the 202 course, we used to convert it by hand. But now we are going to do it using a procedure. Okay? So it's a low-level procedure which does the conversion of an integer which is stored in binary into a string. Yes, Khalid.
Doctor, when we converted from a string to integer, we know when we should stop, right? But
yeah, so
here,
we multiply and we multiply the, let us say, the accumulated sum by 10, and then we add the digit and we repeat. But here we are dividing by 10 to extract the remainder that will be from 0 to 9. It will be a decimal digit. I'm going to show you an example. Just one example. Okay, let me just show you an example, and then I will answer your questions. I can see Mushtaba has raised his hand, but before, okay, so what we need to do is that we need to write a procedure. So this procedure is going to divide the number by 10. And of course, when you divide by 10, the remainder has to be between 0 and 9. So what we need to do is that we need to convert the remainder, okay, into ASCII representation. So we need to convert it into a character 0 to character 9. And this is very easy because we can just add the number 48 or 30 in hexadecimal. And we repeat the division until the quotient becomes 0. So when the quotient becomes 0, then we know that we stop. Because if you continue like this, then you get zeros, okay, to the left of the number, and these leftmost zeros are not significant. We can just simply ignore them. So the digits are computed backwards. It's very important here to highlight backwards, okay, from the least significant to the most significant. Here I have my example. This is an example. So suppose I have the number 2037. Now this number will be in binary. I'm showing it in decimal, but really it's in binary inside a register. So the first step is to divide the register that contains the number 2037 to divide it by 10. Of course, this division is done in binary because the hardware is designed in these circuits. Inside the hardware are implemented to do the division in binary, okay? So when you divide 2037 by 10, you get two values. You get the quotient, this is low, and you get the remainder, which is high. In this example, it will be 203. This will be the quotient, and the remainder is 7. We know that, okay, because I'm showing the number here in decimal. So we get two values, the quotient and the remainder, when you divide by 10. Now, this remainder has to be converted into a character, which is character 7. So we have extracted the least significant digit of the number, okay? So that will be the 7. Now take the 203 divided by 10, you get the quotient equal to 20, and you get the remainder equal to 3. So convert the 3 into character 3. Repeat, divide the 20 by 10, you get the quotient equal to 2, and the remainder equal to 0. Now notice that the remainder equal to 0 is a character. It's a digit, okay? So itself is a digit, but the quotient is still different from 0, so repeat. 2 divided by 10, you get 0 quotient and the remainder equal to 2. So notice that this is the most significant, okay, digit, which is character 2. Now notice that because the quotient is equal to 0, terminate, stop the loop. There is no need to continue because if you take this 0 and divide by 10, you will get actually 0. And the remainder equal to 0. So basically you get zeros to the left of this number. So there is no need for these digits. So stop when the quotient is equal to 0. Here's a function that does exactly what I mentioned, okay? So I'm going to write a function that converts an unsigned integer into a string. So my input is the value in binary. This is the unsigned value. And I'm going to also to have an A1, which is the address of the buffer in memory, because I would like to convert it into a string, and this string will be in memory. So therefore, I'm going to write my digit characters. I'm going to write them in memory. So the string itself is an array in memory. Now I'm going to limit this array to only 12 bytes because that will be the longest integer. Okay. Knowing that we are only using a 32-bit register, that will tell you that how long, what is the maximum length, okay, how many digits you can have, okay, and you can also have one extra byte for the null character, okay. So V0 here will be the address, so the output will be V0, that will be the address of the converted string in memory, okay. So I'm going to initialize P0 to 10, okay, because this is my divisor, because I'm going to divide by 10. Okay, I'm going to start at the end of the buffer. So notice that here, I'm going to add A1 plus 11, okay, using add immediate. So by adding A1 to 11, so notice that A1 here is the buffer address. So I'm going to start at the end of the string and move backwards. Because if you noticed in the previous slide, that the first remainder is the least significant digit, okay? So I'm going to move from the least significant to the most significant. So I'm going to move backwards in my string. So start at the end of the string, store a byte here. We are going to store here 0, the null character, to mark the end of the string. So store a null character, and then start by dividing A0 by 10. T0 is 10. So we get two values. The low here is the quotient, and the high is the remainder. So we put them in two different registers. The quotient is placed in A0 so that we can repeat this loop, whereas the high is my digit. Now the high itself has to be converted into an ASCII character. So we add here 48 to T1, place the result in T1. So now it becomes a character, okay? So once we have it as a character, okay, we need to store it. But before I store, I need to change V0. Now notice that V0 is my address, okay, the address of my string in memory. So decrement the address by 1 by adding -1 so that we can point to the previous character in my string. Okay, so we add -1 and then store T1. Store the character in memory at this address. So we are storing the string in memory, okay? And then branch as long as A0 is not equal to 0. Remember that A0 is what? A0 is my quotient because we are dividing the value here by, so when we move from low into A0, A0 itself is my quotient. So as long as my quotient is not equal to 0, branch back to the loop, repeat. If it becomes 0, let's terminate the loop and we are done. And when we are done, we return back to the caller. So this is my jump register. So this is my function, okay, that does the conversion. Okay, so we are converting an integer, which is stored in one register, a 32-bit integer. We are converting it from binary into a string, a decimal string. Okay, and we use the divide instruction, move from low, move from high. This is to actually to extract the quotient and the remainder. Okay.